Back pain is one of the most common and debilitating conditions in the world, and a major contributor is degeneration of the intervertebral discs, the shock-absorbing structures between the bones of the spine. For decades, disc degeneration was seen as a mechanical problem, the result of wear and tear that erodes the disc's cushioning function. But recent research has illuminated a far more complex picture, revealing that chronic inflammation at the cellular level plays a pivotal role in disc breakdown and the onset of persistent, often severe pain. This deeper understanding of the biology of the spine is changing how we think about and how we might treat back pain at its root. Each intervertebral disc is made up of a tough, fibrous outer ring called the annulus fibrosus and a soft, gel-like core called the nucleus pulposus. In youth, these discs are rich in water, collagen, and proteoglycans, molecules that help maintain resilience and flexibility. But over time, due to age, injury, poor posture, or metabolic stress, this internal architecture begins to deteriorate. The nucleus loses hydration, the annulus may develop small tears, and the disc overall becomes thinner and less effective at absorbing spinal load. However, mechanical degradation is only part of the story. What accelerates and amplifies disc degeneration is an inflammatory response triggered at the cellular level. Damaged disc cells, especially those in the nucleus pulposus, can enter a state of cellular senescence, in which they stop dividing but begin secreting large amounts of inflammatory and catabolic substances. These include interleukins like IL-1S and IL-6, tumor necrosis factor alpha, TNFA, matrix metalloproteinases, MMPs, and reactive oxygen species. This mix, known as the senescence-associated secretory phenotype, SASP, not only breaks down the structural components of the disc but also attracts immune cells into a space that is normally immunoprivileged. This triggers a persistent, self-reinforcing cycle of inflammation and degradation. As this internal inflammation spreads, it causes the disc to weaken structurally and chemically. Proteoglycan loss reduces the disc's ability to retain water, leading to further collapse and bulging. Collagen fibers break down, reducing tensile strength, and as the disc height diminishes, the biomechanics of the entire spine become destabilized, placing more stress on surrounding muscles, ligaments, and joints. The end result is often chronic mechanical pain and nerve compression, particularly when inflammation causes the disc to impinge on spinal nerves or leak inflammatory molecules into nearby tissues. Interestingly, inflammation in degenerated discs often occurs without infection or autoimmune disease. It is driven from within by the disc cells themselves. This sterile, non-infectious inflammation is what sets intervertebral disc degeneration apart from other inflammatory conditions like arthritis. And it also makes treatment more challenging, as traditional anti-inflammatory drugs may not effectively reach or reverse the deep, cellular sources of the damage. Recent research has pointed to senescent disc cells as a key therapeutic target. These cells don't just fail to repair tissue, they actively contribute to pain generation. Their SESP factors can sensitize nearby nerve endings and attract immune cells that release additional pro-inflammatory compounds, worsening local pain perception. In some studies, senescent cells have even been linked to the growth of tiny nerve fibers into regions of the disc that are normally not innervated, essentially rewiring the disc to become more sensitive to pain over time. Because of this, new strategies are being explored that go beyond mechanical fixes like spinal fusion or discectomy. These include senolytic therapies that selectively eliminate senescent disc cells, stem cell treatments aimed at regenerating healthy tissue, and biological agents designed to block specific inflammatory pathways within the disc microenvironment. Early studies in animal models show that clearing senescent cells can reduce inflammation, preserve disc structure, and improve mobility, raising hope for future interventions that treat back pain at its true biological root. Moreover, lifestyle and metabolic factors play a significant role in disc inflammation. Obesity, poor nutrition, smoking, and chronic stress all contribute to the cellular stresses that accelerate disc degeneration. Elevated blood sugar, for instance, can promote the formation of advanced glycation end products, AGEs, that stiffen disc collagen and increase oxidative stress. Addressing these systemic drivers through diet, exercise, and metabolic health optimization may complement targeted therapies by reducing the overall inflammatory load on spinal tissues. In summary, the pathology of intervertebral disc degeneration is deeply tied to inflammation at the cellular level, not merely wear and tear. Senescent cells, oxidative stress, and immune signaling combine to break down disc structure and ignite persistent pain. This evolving understanding opens the door to biologically driven therapies that may offer not just relief, but repair. As science moves closer to decoding the full inflammatory cascade within the spine, we may finally approach a future where chronic back pain can be treated not as an inevitable consequence of aging, but as a manageable, reversible condition rooted in cellular renewal.